Next, we want to find the Maclaurin series for sine of x. So we need to know what the nth derivative for sine of x is. Now, that's kind of tricky since it's not as straightforward as e to the x. So let's take a look at some functions, some of the derivatives of this function. So we've got f of x is equal to sine of x. So f prime of x equals cosine x. F double prime is negative sine x. F triple prime is negative cosine x. And then the fourth derivative is sine x. Okay, and at this point, now we're back to the top. So the fifth derivative is going to look like cosine, then the sixth is going to look like sine, and so forth. Now, since we're looking for the Maclaurin series, that means our a is 0. We are centered at 0, so we need to know what these values are at x equals 0. We'll do a quick unit circle over here. So what are these points on the unit circle? We've got 1, 0, 0, 1, negative 1, 0, and then 0, negative 1. Okay, so our sine at 0 is 0. Our cosine at 0 is 1. Then we have 0, negative 1, 0, and we start again from the top and repeat. So we need to write this. We want to write this in general. How would we write f nth derivative at 0? So to me, this kind of looks like an alternating kind of thing where the coefficients on the even, if I call this even derivatives, are going to end up to be 0. So what I'm hoping for is to be able to write the first one, that's our c sub 0, plus cosine of 0, that's our first derivative, times x over 1 factorial, right? Plus 0 times x squared over 2 factorial, plus negative 1 x cubed over 3 factorial, plus 0 times x to the 4th over 4 factorial, and so on. Okay, so this is our expansion, and I want to write this in summation form. So what do we see? We see that we've got 1 x to the 1st over 1 factorial. We've got plus negative 1 x to the 3rd over 3 factorial. What's the next one going to be? The next one's going to be 1 x to the 5th over 5 factorial, or 5th factorial if you don't know how to speak. Negative 1 x to the 7 over 7 factorial. So how can we write that as a sum? Well, we have negative 1 to the power, right? Negative 1 to the n power, how about? We want our sum to start at 0 and go to infinity. So if we start at 0, that means my 0 should give me this one. So how do I get that? How about x over n factorial? Does that give it to us? Not quite, because our, oh, forgot my n here. Not quite, because if this is to the 0, it would give me a positive coefficient. It would give me a x to the first, nope, x to the 0th, so that my exponent is wrong. And then 0 factorial is 1, but I want it to match that. So let's go with, how about n plus 1? Does that make this thing work? If we use n plus 1, and if I have n equals 0, the first one's positive, okay, so the coefficient works. Now I have x to the first power, okay, that's what I want, and then 0 plus 1 is 1 factorial. So far so good. This works for the first term. Does this work for the second term? The second term should be negative 1 x cubed over 3 factorial. If I use n equals 1, negative 1 to the first power is negative 1. So far so good. 1 plus 1 is 2. 1 plus 1 is 2, so this is still wrong. I need those n's to count by 2's. So I want 2n here, 2n here. Now, when I think about my powers of n, if n is 0, my first exponent is 1. When n is 1, my next exponent is 3, and then 5, and then 7, and so forth. So now I have what I want. Check. In the example in the book, it will also ask for us to prove that x represents, that the sign of x expansion represents the sign of x function, and we're not going to do that. I am mostly concerned with just finding the Taylor or the Maclaurin series expansions for functions and not proving anything to do with them. Please note that there are more details than what we are going to cover in class due to time.